Hi, everyone. My name is Shomo, and welcome to my mini lecture on a topic of artificial intelligence that I'm very passionate about. This is going to be a mini lecture on unsupervised machine learning. This is a course, uh, all the course material has been designed by me from scratch, and I'm just going to give you a quick walkthrough of this. This can be a semester-long course or even sort of intensive workshops over the next or a few days, but I'm just going to condense it in 10 minutes. I'll just quickly share my screen. And yes, hopefully all of you can see my slides. This is unsupervised machine learning. And again, what I'd like to do is start off with a riddle and a puzzle just to get the class warmed up. This, for example, is a visualization. It looks like the map of the world, but it looks very weird. Again, this if this were an actual class that I'm teaching, I would just pause for maybe 30 seconds or 1 minute and ask what is very, very different about this map. I'll just pause here for a few seconds. And as I think all of you will have figured out, what is indeed wrong or interesting about this map is that the size of each country has been scaled by its population, suggesting that there isn't any single good way of visualizing data, but there are multiple ways of sort of visualizing data and seeing it. And unsupervised machine learning really sort of pushes that concept really, really far. For example, there are many ways to represent our three-dimensional world on two-dimensional piece of paper. These are all the different kinds of maps or projections that you can come up with. And again, unsupervised machine learning really allows us to visualize very, very high dimensional data and draw inferences and find patterns from very, very high dimensional data that otherwise would be very, very difficult. There is this traditional distinction between sort of supervised machine learning, where you are trying to predict something, as opposed to unsupervised machine learning, where you are not trying to predict anything. You are just trying to find hypotheses, trying to find patterns, trying to visualize the data and find if anything just jumps out at you. And whatever comes out of unsupervised machine learning is not definitive. Because if it were definitive, then it would be supervised machine learning. So the start of any machine learning pipeline or any machine learning process starts with unsupervised machine learning. You find patterns, you form hypotheses, then you potentially collect more data or do different things with your data, and you can gradually turn it into supervised machine learning. But really, the way that unsupervised machine learning works, as opposed to something like regression, for example, you have a bunch of students, you have different features or attributes for these students, and you are trying to predict a salary. So a salary is, in this case, a label. As opposed to if you have, say, the 50 US states, and you have the number of murders in those states and the number of robberies and the population, you might try to figure out what patterns do these data sets roughly fall into. So, for example, California might have lots of more murders and more population than Vermont, which is very, very rural. My teaching style also emphasizes a lot of animations. So I would initially help students form their intuition around a very, very complex concept, but then I will circle back, give them some more theory, and then some more practicals and animations, and constantly do this cyclical process rather than bombarding them with a lot of theory initially and then doing the practical. So there is this cyclical process called spiral learning, which I really, really embrace. But again, this is a web page that all of you can check out. The link is right here. And this will also be sent out in the email. But this is a web page and a completely interactive web page that I've designed for this particular course that students can interact with. It's sort of like a one-stop shop for students to sort of interact with all this material. And again, the kind of animations that I design in the very first hour of a class, students will play around with this kind of three-dimensional data, and they will see what kind of data it has and what are the kinds of patterns. And I will immediately ask, is there any way that you can look at this data that can allow you to reduce the number of dimensions? So this is 3 dimensions. Is there any way you can reduce it to 2 dimensions? And after playing around with this data, somebody will eventually hit up on the answer that there is one two-dimensional plane along which I can project all the data. And voila, I have turned three-dimensional data into two dimensions. And that is the magic of unsupervised machine learning, in this case, principal components analysis. And again, my class and all these web pages are full of these kinds of intuitions and animations. It's a very, very good way of communicating all these different insights. I also always try to give sort of really highlight very, very important concepts. So, for example, one concept is a label and a feature. Label is something that you are trying to predict, and features are the attributes of this data. And what you're really trying to do is that it might be tempting to think that there are lots of different features or lots of different dimensions in your data, but usually, and that is called the curse of dimensionality. However, there is also something called the blessing of dimensionality, which is that invariably our data lives in a lower dimension. Those dimensions are much, much fewer than something that you might start with. So, for example, if you have a three-dimensional room here, this book, which is sort of a narrow book, exists only in this corner of the room. And if you sort of zoom out, you can only sort of see two dimensions. The thickness of the book can be sort of ignored. And that is what principal components analysis is really trying to do. Again, in my class, I'm constantly trying to impart these concepts and these basics, which is something that I really want to communicate and want students to learn, because once they get these concepts, then they can build up on these things. Another concept that I usually sort of really sort of hammer to students is that, well, if you have 14 dimensions of data, can you just not remove one column at a time, or visualize two of these features pairwise, visualize two features at a time? But then I will communicate that again, the curse of dimensionality sort of comes back to bite us, because that might work for 14 dimensions. But if your data has 1,000 dimensions or 1,000,000 dimensions, the number of pairwise combinations that you're looking at increases exponentially. And this is something called combinatorial explosion. This is also something that I really communicate to students. And again, the idea is that it's not possible to exhaustively plot one feature versus another, but you need something really interesting. So, for example, here is an animation of how PCA works. It's sort of trying to find the line of best fit through this particular data. And the idea is that there is only one particular line. These are custom animations that I've made for my all this course material. And this animation sort of suggests this idea that there is one particular line which will actually capture all the variation or the variance along this direction. Then I need to find another line that will capture all the variance along the next direction. And these two axes are called the principal components. Again, it seems very, very similar to sort of linear regression, except it's not. And I will get to that in a minute. What we are really trying to do is capture the most variance in the data, or minimize these residuals. And that is really the principal concept behind PCA. Again, there are lots of different sort of animations that I use. Again, this is something that's called the Swiss roll data set. Students usually play around with it, and you can quickly see that there is one particular way. If I look at this rather than this sort of head on, then I can see that the data can be nicely separated. Otherwise, it's not. So some of these principal components can be hard to sort of identify, but the math really helps us. And the idea is that principal components are linear combinations of features. However, again, PCA is not linear regression. This is a concept that I constantly communicate to students. There is a big fundamental distinction between linear regression, which is actually a supervised machine learning model, whereas PCA is unsupervised. Without any additional bells and whistles, you cannot make any predictions using PCA. And again, looking at the crime data set, you can quickly figure out different patterns in this US crimes data set. For example, California is sort of an outlier here, whereas more rural states like Vermont and West Virginia are really, really sort of farther along. And again, how far you are along, how far or how close you are in this PCA plot really tells you something very, very fundamental about your data that you simply wouldn't have been able to tell otherwise. My projects also have, there are lots of hands-on projects that I do. Again, you can take a look at this webpage. There are multiple projects that I make students go through to give them sort of a flavor of what it is like to sort of work on a hands-on real-world data set. And there are multiple such projects that I've created. There is one on electronic healthcare records data. There is something on single cell sequencing. And then for some people who are more sociologically inclined from the social sciences or humanities, there is something on the Gapminder data, which is a social sciences data. Again, these are all sort of students that these projects are real sort of available to students. They can walk through these in the class. And again, there is another concept that I really sort of communicate to students. This is the concept of a bottleneck. There are multiple real world case studies. For example, here is a case study that I worked on using biological data that I sort of stepped students through. And again, the idea that I constantly communicate to students that visualizations, except especially more sort of sophisticated ones like Disney, as opposed to PCA, can be very, very misleading, exactly like those maps and cartographs that we saw. So, for example, if I start off with original data that might look like this, there are various knobs and parameters in these algorithms. And if I just play around with these long enough, I can probably see some patterns sort of jumping out, but then those patterns might not mean anything, which really suggests that the onus is upon the students and the machine learning people to really communicate with the people who are giving them the data and sort of see if these kinds of insights really, really make sense. So these insights need to be validated with experimentalists, with people who have the domain expertise, rather than being treated as ground truth. And again, there are many knobs and parameters in these algorithms. So for example, Disney has something called perplexity. And really, that what I communicate in my class is that the number one problem is really communicating these insights to non-technical people like biologists, since high dimensions are difficult to visualize. And this is a problem that comes up not only in machine learning, but this sort of a centuries old problem. I also like to sort of build bridges between like relevant sort of current topics like large language models. So for example, in this class, I will emphasize that while building large language models, the first step is an unsupervised machine learning step where you're compressing all words into fewer sort of numbers. And then you are using these numbers to predict the next word, which is a supervised machine learning step. So I always give them a sense of where the field is headed. I'm always building these connections between what is really, really relevant and topical in machine learning. And again, I would then switch very, very quickly to clustering, for example. And then again, I would have a puzzle. What is wrong with this picture? And then somebody would say, well, it's highly unlikely that you would see the northern lights in central India, which is really the sort of how you would do sort of clustering or anomaly detection, which then is a nice segue into the second part of the class, which is clustering. Again, there would be more animations like these on k-means and things like that. And then I will just quickly wrap up by saying that this is the entire web page. Please take a look through that and go through it. All the material is sort of available on this web page, and this is sort of a one-stop shop for students to do both synchronous and asynchronous learning, because this sort of repository and this web page is constantly available to them. Thank you so much again for your time, and I would be glad to take any questions again. Thanks a lot again.